Alright, example 1. Simplify 3 times the square root of 2 sevenths minus 5 times the square root of 7 halves plus 3 times the square root of 56. And hopefully we all recognize this much of the problem is what we've already done. And we've also done this before, but never in conjunction with those problems. So what we're going to do is we're going to simplify each object, the 3 square root of 2 sevenths, the 5 square root of 7 halves, and the 3 square root of 56 separately in order to create 3 radical pieces that will add or subtract together. And these are, they call them contrived problems. Contrived problems, that just means that they're going to be such that they're going to be able to add and subtract. So expect them to be able to add and subtract. If they don't, you have not simplified things enough. So if we take a look at 3 times the square root of 2 sevenths, that's 3 times the square root of 2 over the square root of 7. All right. The whole number 3 belongs in the numerator with the square root of 2. The square root of 7 belongs in the denominator. We split apart the fraction so that we have a radical on top and bottom individually. Then I put a minus sign, and then 5 times the square root of 7 halves splits apart into 5 times the square root of 7 over the square root of 2. I left myself a gap here to allow for simplification of the blue term. I'm going to leave myself a gap to allow simplification of the green term. And then I'm going to put a plus here, and then leave a gap there, 3 times the square root of. And now, instead of writing 56, what I want to do is I want to do a factor tree. Okay, so 7 and 8 make 56. Also 4 and 14. I'm going to go 4 times 14. 7 times 8 is fine. 7 is already prime. Both 4 and 14 aren't. So if I can create 2 composites, they break down again. It just gets us to the answer quicker. 4 is 2 times 2. 14 is 2 times 7. So 2 times 2 times 2 times 7 is equivalent to 56. For our purposes, though, that's better. All right, so each object has to be established based on what we're dealing with. Forgot to leave myself a gap for this. There we go. Gap here to fix that, a gap there to put numbers in front of that. Okay, so that's my first step of this problem. So if I see this in my book, that's what's going to go on my paper immediately. I go ahead and break up the objects, and I leave these gaps to allow myself some room to work. And then I'm going to fix each fraction. So the first fraction, the problem is the square root of 7 on the bottom. Multiplying the square root of 7 times itself gets rid of the square root of 7. Fractions require that if you multiply the bottom by something, you multiply the top by the same thing. Moving on to the green fraction, the problem is the square root of 2 on the bottom. I fix that by multiplying by the square root of 2 on the bottom. Again, if I multiply the bottom of a fraction by something, I'm required to multiply the top by something, the same thing. And for the third object, we got a bunch of stuff inside the radical. So pull a pair of 2's out as a 2. The 2 and 7 don't have pairs, so we leave that inside the radical. So what we end up with altogether, the blue term, on top I've got 3 outside the radical. Inside the radicals I got 2 times 7, which makes the square root of 14. On the bottom, the square root of 7 times itself just makes 7. When you multiply a radical by itself, you get a whole number. Moving on to the green term. 5 times no other whole numbers. Inside the radical, square root of 7, square root of 2 makes square root of 14. On the bottom, square root of 2 times itself makes 2. And finally, the red term, we pulled a 2 out. 2 times 3 outside makes 6. 2 times 7 inside makes 14. And that's going to go over 1. I want to create a fraction out of this. Since everything else is a fraction, it's good that everything's a fraction. And what should happen at this point is all those radicals should be exactly the same number. If they aren't, look at the bigger numbers, and they probably reduce the same way this square root of 56 reduced. All right? And one other thing I want to bring to your attention is going to happen very shortly. I can't remember if it's this lesson or in an upcoming lesson very shortly. But suppose this said the square root of 18. Square root of 18 is 3 times the square root of 2. So if some of these radical things here break down like that, you need to do that in this step. From here to here before you worry about this whole radical in the bottom thing. Or if that said 2/9, what's the square root of 9? 3. So just make it 3. Don't make it square root of 9, and then you got to multiply by the square root of 9. Square root of 9 equals 3. So if you get a nice pretty number like square root of 9 there, that equals 3. You don't have to do this step here. Just make it 3, and then you're ready to go. All right? So again, if you get to this step here, once you fixed everything and these radicals don't match, chances are you didn't see a perfect square within the work up here, so just simplify these down. All right? Now, once I get to this point, I just have to create a common denominator. Let me just clarify one thing real quick also. You cannot get rid of the fractions on these problems. There's no equal sign in this problem. Okay? What some of you believe is this. If I have 1/2 plus 2x equals 3/7, if I have that problem, I can multiply everything by 14 to get rid of the fractions, right? Because it's an equation, that's legal. 14 times 1/2 is 7, 14 times 2x is 28x. 14 divided by 7 is 2 times 3 is 6. That's an equivalent equation. That's legal. If I've got 1/2 plus 2/3, I got to get a common denominator and add them up. There's no equal sign. There's no way to get rid of fractions in an addition or subtraction of fractions problem. So if you do this times 6, you've created a different answer, a different number. Where here you've created a new equation that has the same answer. Multiplying this by 6 would create a different problem, which is not correct. So you cannot get rid of fractions in this. All I'm doing is adding and subtracting fractions. I'm trying to get a fraction sum or difference here. I cannot make the fraction disappear. All right, so keep that in mind. The common denominator of these things is 14. Each fraction has a numerator. So what I have to do is take the numerator that I have and fix it to make the denominator I want. So 3 times the square root of 14 is the numerator I have. What do I multiply by? I get 2, because 7 times 2 makes 14, so the blue one times 2. Times 2 on the bottom, times 2 on top, makes what we want. The green one has a numerator of 5 times the square root of 14. What do I multiply by? By 7, right? 7 on the bottom to make 14, 7 on top then. So again, same basic thing I was doing up there. If you multiply the bottom by something, you got to multiply the top by the same thing. What about the red one? It's 6 times the square root of 14.
14.
Times 14. That makes what we want. So we have to do it on top. Alright? So just fix each fraction. Make the denominator what you want it to be. Each denominator needs to be multiplied by something to make what you want. So the tops have to be multiplied by the same thing to allow that to happen. And then what's left to do is to simplify. All the stuff on top will add and subtract because they'll have square roots of 14. So 6 square root of 14 for this one, minus 35 times the square root of 14 for this one, plus 84 times the square root of 14 for this one. For me personally, I like to add the positives and then subtract. So 90 minus 35 is 55. So 55 square root of 14 over 14 is the final answer. Positive because 90 is bigger than 35. Subtracted 90 and 35 because the signs are opposite. So that 90 minus 35 subtracts. Square root of 14 is what's in the radical. Once you get square root, it's the same. It just kind of stays the same all the way through. All you're really dealing with is the fraction addition at that point. And the last thing to look at, does this reduce? Only 2 and 7 go into 14. 2 does not go into 55, nor does 7, so it doesn't reduce. It doesn't matter about the radical number. Only worry about these numbers.